Okay, let's begin. Questions on the homework, 9.1 and 9.2.
19, 21, 22.
This is 9.1 we're looking at?
Yeah.
19. What was the question?
He gave you like two graphs and
Use the graphs to sketch the parametric curves. Indicate with arrows the direction in which t increases. Okay, so 19 was this guy. Goes through -1, and this goes through 1. Can you figure out a rectangular representation for this curve?
X equals t squared minus 1.
Y equals x squared minus 1 is what you'd think. And you can actually use that as a parameterization. Let x equals t, and then y equals t squared minus 1. That's it. And as t increases, you will move in this direction.
That's the graph of x versus t graphs.
The what?
Oh yeah, two graphs, one for the x and one for the y.
X cube. The X cube was
Oh, this is x versus t. Okay. Well, then that's even easier, because you can just look at this and then that's your x. If this is x versus t, then that means your x is t squared minus 1. And then this one,
y equals t cubed.
if this is y versus t, then your y equals t cubed.
Yeah.
So you use the graphs of this and this to sketch the curve. Okay, how do you sketch, how do you combine those? How do you sketch one into the other?
Set up a table.
You could do a table, sure. Another option?
T equals radical x minus 1 and put the
Eliminate y.
Yeah, we can solve for one of these t's. I'd probably solve for the t over here, because solving for the square is going to give me a plus or minus. I'd probably want to avoid that. But here I can get that t is equal to y to the 1/3, and then plug this into here. So then we would graph x is equal to y to the 2/3 minus 1. Which, there are several ways you can graph that. I don't know which you prefer. You could actually think of this as a function of y. So I can add 1 here, and y would be the square root of this cubed. So you graph either one of those. So what does the graph look like?
Sideways being
Like
Yeah.
the quack. Which side would it be on?
left.
Right, so when y is 0, x is minus 1, so it's going to be here. And as x gets bigger, y gets bigger, so it's going to look like this. And now as t gets bigger, what's happening? Yeah, but you're supposed to draw, like what I did here,
That's my
draw an arrow on that curve to show me what's happening when t increases.
Increase.
Right, you can see as t gets bigger, your x gets bigger and your y gets bigger, so your x and y value are getting bigger, that's your direction. So that's that. 21 is the same kind of thing. let's actually move on, because that's not something you'd be asked actually. It's a nice conceptual exercise though. Um,
22.
okay, matching is something we need to do, but then you want to draw these on the board. Let's skip that one, because again, that's not something I'd ask you. But although it is actually a nice exercise to try, I don't want to waste the time on it. They didn't ask you to differentiate anything, or
No.
That was the next one.
The next one was calculus.
Which one was the calculus?
yeah, so this is the boring section. Any questions on 9.2? Because this is stuff I will ask you about. The calculus with the curves. What does that say?
You're trying to find the length of the curve. It's x equals t minus 2 sine t, and y equals 1 minus t cosine t, between 0 and 4 pi.
Okay, how do we find arc length? This is something you should know. A problem like this could show up.
The square root of
The square root of x prime of t squared plus y prime of t squared. And then you integrate between the given limits, 0 to 4 pi. And what's x prime of t? X prime is what? 1 minus 2 cosine. I'm going to square that. Then I'm going to have 1 plus 2 sine. I'm going to square that. Now hopefully this simplifies to something nice.
Why is it 1 plus this? That's just a 1.
Oh, that's a 1. Yeah, so it's just 2 sine. So what do we have here? 1 minus 4 cosine t plus 4 cosine squared plus 4 sine squared dt. Right? 4 cosine squared plus 4 sine squared is what? That's just 4, which I'm going to add to that. I'm going to get 5. Can I do anything here?
Use calculator.
Use calculator.
No, that's what it said.
Yeah, it's a calculator problem. It's not something. So you pretty much stop there. This is probably one of the problems where they'd say set up the integral to find the limit. Just to integrate that is annoying.
And then,
Can we do it though? Like
can we use
with
the
our
calculator?
There's a technique that might work, but I actually didn't teach you guys. It's called a Weierstrass substitution. You could probably try it. Don't worry about it. It's sort of like a reverse trig substitution where you use the arctangent function. It's crazy. Don't worry about it. Other questions? Any other questions? No? So weren't there any about like horizontal tangent lines or vertical tangent lines or find the derivative or something?
Yeah.
And you're all okay with that?
Yeah.
Okay, great. I guess let's just move on then. Talk more about polar. You can pass the homeworks up. Missing something. Let's continue with polar. Where do we pick up? Okay, what were the important equations that we needed to do with polar coordinates?
X equals R cosine theta.
Tan theta would be y over x. R squared is equal to?
X squared.
Okay. All right. Once you're doing polar, these equations have to be in the forefront of your mind. You always have to be thinking about those. In polar, what is the R? How do we think of that? The radius or distance from the origin, and theta is angle made with what? The positive x-axis, right? R we can think of as a net distance. If it's negative, what does that mean? It means you travel in the opposite direction. You sort of walk backwards whenever your R is negative. Okay, just some concepts that we need to keep in mind. Last time we were graphing some curves and we talked about how circles look. In particular, we know that circles in polar coordinates, they would look like either R equals a constant. That would be a circle centered at the origin. If you're not centered at the origin, you would look like A sine theta, or you would look like B cosine theta, or a sum of these two, A sine theta plus or minus B cosine theta. And to figure out what kind of circles these are, you just multiply through by R. You change the R squared to X squared plus Y squared. You change R sine theta into Y, R cosine theta to X. You bring everything to one side, complete the square, you get the equation of a circle. Okay. So those were our circles. What else did we talk about? We also graphed sine 2 theta. Okay. I quickly did that trig function example when we were leaving. Let's do a bunch more of those, because those are the kinds that you're going to be asked. They're very common to ask that, and your final is going to have something like that. So I just want to do a few more examples of that, make sure that we know how to do that. We need to remind ourselves of how to draw graphs, trig graphs in the first place, and then we can move on and talk about calculus. Sketch. R equals 2 cosine 3 theta. So how do we do this?
You graph it first.
We graph it as a trig function first, right? Actually graph R versus theta. What would that graph look like? So the baseline is 0 because that's the constant that's added. The amplitude is what?
Amplitude is 2.
Is 2. So that means you go up 2 and down 2. Right? So then there's going to be this whole grid. Right? Between 0 and 2 pi is what we care about. Now if I have cosine 3 theta, what does that mean? There are 3 cosines in the 2 pi section. So I split that into 3 equal sections, and each section I know cosine and sine come in 4 equal sections on their own. So this would be 4 sections here. 4 sections here. So in other words, I divided 2 pi into 12 sections, which means the length of each section would be what? Pi over 6, and this would be 2 pi over 6, 3 pi over 6, which is pi over 2, 4 pi over 6, 5 pi over 6, 6 pi over 6, which is just pi, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6 is 2 pi. Right, so I already know what those guys are. And we remember how the cosine behaves. Cosine actually starts at the top, and it hits the middle, then it hits the bottom, then it hits the middle, then it hits the top, and it repeats this pattern. So that's our graph. Now we're going to translate this to the xy plane. How did we set it up? The first thing I'm going to draw is what? The circle, right? What radius do we draw the circles? The guys that show up on the vertical axis, right? So 2 and minus 2 corresponds to 2 as well. So the only thing I have here is a circle of radius 2. Okay. And then I'm going to need all these angles that I just wrote. So my base angle is pi over 6, so I'm going to cut this up into 6 pieces. So it's kind of like I'm taking this graph and I'm wrapping it around the xy axis. And so here's my pi over 6, 2 pi over 6, 3 pi over 6, which is pi over 2, 4 pi over 6, 5 pi over 6, 6 pi over 6, which is pi, 7 pi over 6, 8 pi over 6, 9 pi over 6, which is 3 pi over 2, 10 pi over 6, 11 pi over 6. And this is 0, which is equivalent to 2 pi. Okay. Now we're going to start where? 2. Right, when theta is 0, my distance from the origin is at 2. Right? Now remember how our angles increase, it goes counterclockwise. So we're always going to be moving in a counterclockwise motion when we're drawing these curves. Right? So we go from 2, when theta is 0, we're at 2. When I move to pi over 6, what am I doing? I go to 0, right? So my distance from the origin should be 0. So here, I'm going to go like boom, hit the origin, right? When I'm at an angle of pi over 6. From pi over 6, I'm going to move to 2 pi over 6. When I'm at 2 pi over 6, my distance is minus 2, right? So 2 pi over 6 is this angle, right? So what does my distance of minus 2, what does that mean?
Go down to quadrant 3.
Right, I don't go towards 2 pi over 6, I go in the opposite direction. So where am I going to go?
7 or 8.
The 8,
Yeah.
right? So instead of going towards the 2, I go in the opposite, so I'm going to go down here. I'm going to hit that 8, right? That's when I'm here. Then I'm going to come back to 3 pi over 6, I'm back at the origin, so I'm going to loop back to the origin. Then 4 pi over 6, I should be on the circle of radius 2. So I'm going to go jump up here, circle of radius 2. 5 pi over 6, I'm back at 0. So on the angle of 5 pi over 6, I should come back to 0. 6 pi over 6, which is pi, I go to minus 2. So I don't go towards 6 pi over 6, I go in the opposite direction. I come over here. Then for 7 pi over 6, I come back to 0. 8 pi over 6, I go 2, but you see that's already filled in. Right now I'm just going to retrace this loop. I come back to 0 at 9 pi over 6, then for 10 pi over 6, which is here, I'm going to go to the negative, I'm going to retrace that loop, and then by the time I hit 2 pi, I come back here. So it's really just 3 pedals. That's my graph here. I have 3 more examples, so if you don't get it, you will see eventually. So, might be a little shaky, but let's do another example. Sketch 3 minus 2 sine theta. Is there a question? Yes?
It is too quickly.
What? What is?
How do we know the number of the pedal? How do you determine it?
Oh, there's a rule that says if it's odd, that's the number of the pedals. If it's even, it's double the number of the pedals. If it's a cosine, there are things like that. There are rules you can memorize. I never memorize them. I don't like memorizing stuff. Once you draw this, you can figure out, you can just naturally figure it out. So I never bothered to memorize this. But there are rules. They're in the textbook if you're interested. Okay, how would this one look? 3 minus 2 sine theta. Right, so 3 means we shift everything up. So I go to 3, and that's my baseline. That's like my center line. And what's my altitude? Is 2, which is the coefficient. So from 3, I go up 2 to hit 5. I go down 2 to hit 1. That's my highest point. That will be my lowest values. And there's just a 2 pi. Like this is theta, so the period is just 2 pi. I would divide that into 4 sections. So it's the usual kind of way we break it up. 0 pi over 2, pi, 3 pi over 2, 2 pi. And this is, how would this graph look? It's a sine, so it starts in the middle, and then what are we going to do? We're going to go down because it's a negative sign, so it's the opposite. Then we go back to the middle, then we go to the top, then we go to the middle. Right, so that's what one period of that graph looks like between 0 and 2 pi. Right, and I when we did that trig review, I told you guys how to determine the amplitude and the period and the phase shift and all that. So if you forgot any of that, you should look it over. So yeah, let's go to the XY plane and see what this graph looks like. Okay, so what's the first thing I do? I need to put my circles in. What radiuses will we put? Radii. This is theta versus r. I need a radius 1, a radius 3, and a radius 5, right? My main values on my y-axis will give me those radii. So there's a radius 1, there's a radius 2, 3, sorry, and then there's a radius 5. I only have the normal angles, so there's 0, there's pi over 2, there's pi, there's 3 pi over 2, and there's 2 pi. Okay, so how do we start? When theta is 0, where am I? At 3. So when theta is 0, I'm on the circle of radius 3. So I'm right here. Okay, now what? As I move to pi over 2, what happens? Decrease. I go to the circle of radius 1, right? At pi over 2, I'm on the 1. So I'm going to jump to the circle of radius 1. Now when I'm at pi, what do? I jump back to the circle radius 3. So now I'm here, right? When I hit pi. When I hit 3 pi over 2, where am I? On the circle of radius 5. So when I hit 3 pi over 2, I'm going to jump all the way down to this circle. Right? The numbers tell you what circle you should be on, right? Circle radius 1 versus circle radius 3 versus circle radius 5. And then when I'm back at 2 pi, I'm back on the circle radius 3. So that's your curve. It's kind of like an egg, an upside down egg. That's what it should look like. That's the polar curve for that one. Let's do another example. One plus 2 cosine 3 theta. Okay, let's start by graphing this trig function. What does the graph look like? Baseline is at 1. That's my center. Amplitude is 2, which means from 1 I go where? I have to go up by 2 and down by 2. So I go up to 3, go down to minus 1. That's my highest point, my lowest point. Here's where 2 pi happens. That 3 means that's the frequency. There are 3 cosine graphs. This looks just like the first one. So there are going to be 3 equal sections here, and each of those I split into 4 equal sections. Ultimately, there are 12 equal sections, which means the sections go like pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 2 pi. Right? Now I'm going to graph the cosine, which means he starts at the top, goes to the middle, and goes to the bottom, and goes to the middle, then goes back to the top, and repeats that pattern. Okay? Now what? Now what? There's something else we need first. The zeros. Right, remember, whenever you hit 0, that's an important point. That creates loops. That means you go to the origin, you go somewhere else, and you come back to the origin. Right? We need to know when our loops form, because I'm going to be asking about loops later on. So I need to know where are the zeros. Right? So I just said 1 plus 2 cosine 3 theta equals 0. How do I solve that equation? Cosine 3 theta equals minus a half, which means 3 theta must be equal to what? No, cosine pi over 3 is positive a half.
4 pi.
Which one? What? Right. So we're looking, we know pi over 3 is one of them, right? So what does that mean? What do you do with that pi over 3? It means you divide pi into 3 pieces, right? Boom, 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 boom. Right? The important parts are the angles that are closest to the x-axis. So this is important, which is pi over 3. This is important, which is 2 pi over 3. This is important, which is 4 pi over 3. And this is important, which is 5 pi over 3. Right? And you just count those off. 1, 2, 3, 4, 5, 6 pi over 3s. Right? Now, we have to remember that mnemonic, all students take crack. What? Say calculus, come on. What are you thinking about? Okay, so where's the cosine negative? On these two. So I know the answer to this means it has to be 2 pi over 3 or 4 pi over 3. Here's the thing though, how many zeros do I have? 1, 2, 3, 4, 5, 6. So I need the first 6 answers, right? These just give me the first 2, right? But the answers will always be in these quadrants, right? So how do I know what they are? Just keep counting, right? So this would be 6 pi over 3, 7 pi over 3, 8 pi over 3, 9 pi over 3, 10 pi over 3, 11 pi over 3, 12 pi over 3, 13 pi over 3, 14 pi over 3, 15 pi over 3, 16 pi over 3. Right? That's my first 6 answers. Just keep counting. And so now, if my 3 theta is equal to that, right, then my theta is just what? Just divide by 3 everybody. 2 pi over 9, 4 pi over 9. Now don't be scared that those look like weird angles. You just know that their relative positions are, right? Like this guy is somewhere between pi over 6 and 2 pi over 6. That's all that really matters. Right? We're just doing a sketch. We don't have to be super accurate. Okay, so now let's do the sketch. Will I have space? We'll make space. So I need circles of radius 1 and 3. These, by the way, should be very faint. They're not a part of your graph. I'm just sort of graphing them harder than I would normally, but I want to make sure that it shows up on the camera. But the circles are very faint. They're like the skeleton. They're not really a part of your graph. Right? They're just guidelines. Okay, so and we go through that whole process again. We have to put in all our angles that we care about, which pi over 6 is how things are split up. So I'm going to divide pi into 6 pieces. Continue that process down here. So here's my pi over 6, 2 pi over 6, 3 pi over 6, which is pi over 2, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6, which is 0 or 2 pi. My zeros occur where? There's one between pi over 6 and 2 pi over 6. So there's one here. That is 2 pi over 9. There's another one between 2 pi over 6 and 3 pi over 6. So that's here. That guy is 4 pi over 9. There's another 0 between 5 pi over 6 and 6 pi over 6, which is here. That guy is the 8 pi over 9. There's another 0 between 6 pi over 6 and 7 pi over 6, which is here. That is my 10 pi over 9. There's another one between 9 pi over 6 and 10 pi over 6. It's here. This guy is my 14 pi over 9. The next guy is my 16 pi over 9, and he ends up between 10 pi over 6 and 11 pi over 6. So this is 16 pi over 9. So I have all those angles to worry about. Okay, so how do we start?
3.
So when my theta is 0, my r is 3. I'm on the circle of radius 3, so I'm out here. Okay. Now what do I do? The first angle I hit is pi over 6, and where should I be? On the circle of radius 1, according to that. So I'm going to go from here and jump there. Then I'm going to hit the 0 next, right? Which happens at this 2 pi over 9. So I'm going to make a sharp turn right here. Now I'm at the origin. Then I go to 2 pi over 6, right? Just 2 pi over 6. But it's negative, I have to go in the opposite direction. What's going to be the opposite? The 8, right? So I'm going to go down towards the 8. Then I'm going to come back to 0. Right? So I made a very tiny loop here. Right, so far this. Now I'm at the 0. I'm right here. Right? So my next angle I hit is 3 pi over 6. Where should I be? On the circle of radius 1. Right? So 3 pi over 6 is this angle. I'm going to jump back to the circle of radius 1. So I'm going to make that little jump here. Then what?
You jump up again.
I move to 4 pi over 6. That's going to jump me all the way to 3. So 4 pi over 6 is all the way up here. I'm going to jump to the circle of radius 3. I don't know if you can tell what this is going to look like yet. It has big loops and small loops. Okay. So I thought that would be nice. Okay, so 4 pi over 6 is right here. Our next angle we hit is 5 pi over 6, and we're on the circle of radius 1. So I'm going to come to this angle, and I should be on the circle of radius 1. Then I move to, I hit a 0, right? My 0 is going to be that 8 pi over 9. So I go back to the origin here. Then I go to pi, 6 pi over 6, right? But I don't go towards it, I go away from it because my r is negative. So I go in the opposite direction, and I'm going to jump to the circle of radius 1. So it's going to go here. Get that jump. Then I'm going to come back to 0. Wait,
6 pi over 6.
then I'm going to hit the 0 again. I'm making a very small loop again here. Where am I?
It should be
It goes
a
to
0.
That's the wrong line.
The y should be a 0.
I forgot what angle we're on. So this is
5 pi over 6.
5 pi over 6. We were here. Then we went to the 0. Then we went to 6 pi over 6. We jumped on the circle of radius 1. It should be on the horizontal. That's why I see preference. Then I'm going to come back to 0. So now I'm here. Then I'm going to jump back to the circle of radius 1 at 7 pi over 6. So 7 pi over 6 is over here. Then I'm going to jump to the circle radius 3 at 8 pi over 6. 8 pi over 6 is over here. Then I'm going to jump to the circle radius 1 at 9 pi over 6. 9 pi over 6 is over here. And I'm at the circle radius 1. Then I'm going to hit that 0. Do you sort of see what's happening?
It's 3.
Then we're going to, I'm at this 0. Then I'm going to go to my 10 pi over 6, which is here, but I'm going to go in the opposite direction. So I'm going to come here, hit that little loop, come back to 0. Then I'm going to jump to 11 pi over 6, circle radius 1. Then at 2 pi, I go back to 3, and I close out the graph. It's like I have 3 loops, and then 3 little loops inside it.
Can you like wing it and like you know halfway?
Yeah, I mean, it's not, well, you should be between whatever angles you're supposed to be between. So that you have to make sure you're very careful. So yeah, that was a graph that looks like this, 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 and then you put 3 little loops on the inside.
Is this okay?
You can get all sorts of weird graphs from these polar graphs. They're really nice. You can get a lot of cool stuff from it. Very psychedelic, trippy stuff. I thought that one was a nice example to close on. You wouldn't get, like the one on the final wouldn't be that hard, but I just thought that was cool. Common shapes that show up on like a final, yeah, like this oval, possible to get. You'd also get things like where there are like a loop inside it. Of course, flower petals, those are pretty popular. You'd also have things like heart shapes, something like that. You'd also have things like, yeah, that's me saying a little. Okay, there are also things where you might have a flower, and then you have little loops in the middle. Those are possible. Like, one of the loops is the inside. I don't think those show up very often. But if it does show up, it's the same principles to draw any of these graphs. But you can get some amazing graphs using polar coordinates. And they look pretty simple when you look at them in the
How long
bar theta.
would you think this problem will take?
What?
How long would you think this will take on an exam? Like you should focus. Like I gotta time myself.
Yeah, I can actually give you an exact time if you'd like.
Like 10 minutes.
And if I have a final here, I can tell you. It'll be closer to 7 minutes.
What?
Somewhere between 7 and 15. Yeah. So 7 to 15 minutes, depending on how it is. Basically, the rule is each question on the final is you have a 15-minute time window to do it. It's possible to get one of these as part A in a 2-part question, in which case you have 7 minutes for this and 7 minutes for the other one. But it's also possible, there are finals where this is an entire question, so on a final like that, you get the whole 15 minutes. I think your final is one like that, but I'll tell you that closer to it. Yeah.
Are your finals similar to the format of the finals?
Yeah. Next week I'll tell you what it's gonna look like what format-wise, sort of things you have to know. I don't think we'll have a time for a final review, but I'll give you some, hints on what I think it's important for you to know. I wrote the final. I already wrote the final a while ago.
The first week.
Yeah, because no, not the first week. The course supervisor for this class she likes to get things way ahead of time. So I wrote it and I sent it to her for approval, and I'm waiting to hear from her to say, yeah, you can go ahead. So
She's gonna say it's too hard.
no, my tests are never too hard. Yeah. So as soon as she gives me the green light, then I can say, okay, I definitely know this is what your final is gonna be like, and I'll tell you. Not the exact questions, of course, but just some ideas. But I can tell you, yeah, something like this I wouldn't put on it, like loops inside of loops. But yeah, something like what I drew over here, like things like that, you should know. How much time do we have? Not much time. Okay, let's get through this. So those are the graphing questions. It's guaranteed that you'll get something like this on the final. It's guaranteed to come on the fourth test as well, just to make sure you have practice with it. So make sure you know that. Things like matching graphs, like I'm not going to ask you that. Now let's talk about calculus with polar coordinates, which Calc 3 will pick up with this, with force, but let's look at the basics. Calculus with polar coordinates. So we're going to find out how to take derivatives, and we're going to do some things with integrals as well. So typically we think of r as a function of theta, just like you see me say here, like r equals blah, 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 theta. Theta is usually thought of as the independent variable and r is the dependent variable. So we usually write like r equals f of theta, right? You can think of it that way. So since x equals r cosine theta, this means I can think of x as f of theta times cosine theta. And since y equals r sine theta, I can think of y as f of theta times sine theta. Now what you'd realize with this, what kinds of equations are those? Those are parametric equations. With parameter theta. Which means all my rules that I told you about parametric equations, they will apply here, right? It's just that now theta is my variable instead of t. So you can pretty much go over all the rules I mentioned from the previous section and just apply them to this, and you can figure out all the answers that way. However, I'm going to give you some other formulas if you care to memorize them. It's quicker to memorize them, but it's not essential. But it's because we know there's a sine and a cosine, we sort of know what the formulas look like ahead of time. So for example, if I ask you about what is the derivative dy dx, well, from parametric equations, I know that this is dy d theta divided by dx d theta, right? Which gives me the following. I just do the product rule for the f and the product rule for y, and just put them on top of each other, right? So this would be f prime sine theta plus f times cosine theta over the dx dt, f prime cosine theta minus f sine theta. Right? So in polar coordinates, if you're thinking of your x, y in polar coordinates, that's what the derivative looks like. Right? That formula. Like I said, you can memorize it if you want, but it's not terribly important. If you remember this relationship, you can figure out that relationship. It's not. Right? Just plug in whatever function I give you here and find its derivative, put the derivative of y on top, the derivative of x on the bottom. Right? Same old rule, I just wanted to rewrite it in a different form. So that's what it's equal to, provided, of course, dx d theta is not equal to 0. It's equal to 0. We could have a vertical tangent line. We could also have something else happening. first formula. Similarly, and by the way, this would be what the derivative looks like for the pictures that I was drawing, right? So if I wanted to find out the slope on these petals that I drew, this would be the formula I would use. Depending on what my theta value is, I can figure out what my derivative is, right? So similarly, we have a vertical tangent line, just where you expect, vertical tangent line if dx d theta equals 0 and dy d theta not 0 at the same time. We have a horizontal tangent line if dy d theta equals to 0, but dx d theta is not 0 at the same time. If both dy d theta and dx d theta are 0, these limits with L'Hopital's rule find the derivative at that point. So if both equal 0, use a limit to approach that point. And since the top and the bottom are 0, you can use L'Hopital's rule and find a limit if it exists at all. What else? Okay, I gave you an example. Find the points where this graph r equals sine theta has horizontal tangent lines and vertical tangent lines. Part 2, what is this slope? When theta equals pi over 3, I think. Yes. I'll ask a problem like this on your 4th test, but I don't think I put something like this on your final. But if the course supervisor complains, you should have one of these problems on the final, then I'll put one on the final. But I didn't. I test you on parametric equations, but I test you in the first versions, mostly. With polar, I'm mostly going to ask you to graph and find areas, which I'm going to cover soon. But if this ends up being put on your final, you should know how to do it. It's not that bad. You still follow the same old rules from 9.2. Now you just have thetas instead of t's. That's basically it. So what do? Let's figure out what is x. What is our x? X is r cosine theta. And what is our r? Sine theta. So x is, in this case, my x is sine theta cosine theta. What is my y? What's r sine theta? Right? Which means my r is actually sine theta, so my y becomes sine squared theta. Which means I care about tangent lines, so let's find the slope. dy dx is just dy d theta divided by dx d theta.
We write x as 1/2 sine 2 theta. I think that would work with finding this derivative.
That is completely okay in my book. I would not. Totally fine. Right? So you don't have to do the product rule. You can sort of do a little chain rule and it's nicer. That's totally fine. So dy d theta, I just differentiate this with respect to theta. What do I get? Two sine theta times cosine theta. I'm telling you guys, I forgot how to differentiate that. She's like, we've been doing so much that I forgot how to. I don't even know how to write my name anymore. Okay, what's dx d theta?
Cosine theta.
Differentiate this.
Cosine theta.
So it's cosine 2 theta times 2 by the chain rule, which kills that half. So what does that give us?
Tan 2 theta.
Tan 2 theta. Right? That's our derivative, because 2 sine theta cosine theta is sine 2 theta. Okay? So that's our derivative, tangent of 2 theta. So now A, let's do horizontal tangent lines. Where do those appear? This means dy d theta equals 0, right? Or in other words, tangent of 2 theta equals 0. Means 2 theta must be equal to what? What are the values that give us 0? 0. 0. What else?
No. No, pi.
What? Pi. 2 pi. 3 pi. Every multiple of pi, right? N pi, plus or minus. Right? So pretty much n pi. Right? Remember, tangent is 0 when the sine is 0. Sine is 0 at every multiple of pi. So n pi is when this guy will be 0, right? Where n is any integer. Which means my theta would be n pi over 2. So it's going to be every multiple of theta plus all the half multiples of theta. So those are the points that will give me 0.
But
Yes.
why dy d theta is tangent to theta, not sine to theta?
Well, this equals 0 means this equals 0 at the same time. You could look at it this way. They're both equivalent statements. Right? A over B equals 0 also means A equals 0. They're equivalent statements. Right? Saying this is 0 is the same as saying that is 0. And if that is 0, then this is 0, vice versa. Okay? So these are all my guys. So I can have 0 plus or minus pi over 2 plus or minus pi plus or minus 3 pi over 2 plus or minus 2 pi, etc. Right? All values like that, I will have 0. Are there an infinite number of points which I would have a 0 tangent line? No. Let's figure out what the points are, right? So I know these are my theta values, which means start picking one, right? So let's say theta equals 0. This means my x is what? X is this. If theta is 0, what is my x? 0. What is my y? It's also 0, right? So 0 comma 0 is one place I will have a horizontal tangent. Say theta equals the next one, say pi over 2. Plug in pi over 2 here, what do I get? X equals 0. Plug in pi over 2 over here, what do I get? Y equals 1. So 0 comma 1 is another point I will have a horizontal tangent. And you keep doing this. You won't have an infinite number. Eventually, you're going to repeat a value, and that's when you stop, right? So let's do another one. If 0 equals pi, right? I'm just counting in the forwards direction, because whether I go forwards or backwards, I'm going to get the same answers eventually. So 0 pi over 2, pi, 3 pi over 2, 2 pi. I'm counting forward like that until I get a repeat. So this is also going to give me both of these guys zeros, right? 0, 0. So I'm already starting to repeat. Does the next one repeat if I put 3 pi over 2? 3 pi over 2 is going to make this 0. 3 pi over 2 will also make the sign, it'll make the sign -1, but I'm squaring it so I'll get +1. So I'm going to repeat that value. So yeah, it's going to keep jumping between these two values. So those are the only 2 points where my tangent line is horizontal. Okay. Do the same process again for the vertical. So let's look at vertical tangent lines. So this means I need dx dt equals 0. Which means, what are my values? Oh, did we check? We should have checked where dx dt was 0 here as well. We'll see if there are overlaps. We'll have to weed those out.
dt and theta.
So what?
Theta.
D theta.
D theta.
Not D.
D theta. So that means what? Where's my dx dt? Cosine. This means cosine of 2 theta equals 0. Where's the cosine equals 0? N pi over 2, where n is an odd integer. Right? So my thetas will have to be n pi over 4s, where n is odd. Right? So my possible theta values here are plus or minus pi over 4, plus or minus 3 pi over 4, plus or minus 5 pi over 4, etc. Right? And now I'm going to test each of those values. Just pick one and just start increasing until you start seeing repeats. So let's say my theta is pi over 4. What is my x value? What is this when theta is pi over 4? 1/2. What is my y value when theta is pi over 4? It's also 1/2. What? Right? 1 over radical 2 and you square it. So 1/2, 1/2. Notice that these don't overlap, which was important. I should have checked that before. But, okay, so I move to the next one. What about 3 pi over 4? What is my x value at 3 pi over 4? Plug in 3 pi over 4 here, I get 3 pi over 2. Sine of 3 pi over 2 is -1 times 1/2. That's minus 1/2. Plug in 3 pi over 4 here. What do I get? 1/2 again, right? 1/2. Right, because I get 1 over minus 1 over radical 2. So this is minus 1/2, comma 1/2 is the next point. This is going to repeat again. But if I plug in 5 pi over 4, right, you're always going to get like a plus or minus 1 over radical 2. At 5 pi over 4, we're in the third quadrant, right? The sign is going to be negative. So that's going to repeat that one. This guy's going to keep giving us 1/2 either way, right? So this guy's going to jump between plus and minus as well. So we only have those 2 points. So these are the points where I have vertical tangent lines. Could we have figured this out some other way?
Couldn't you sketch the graph?
You could have sketched the graph, right? What do we actually know what r sine theta looks like. It doesn't, it's not that hard. We've actually drawn that one before. Remember, we multiplied through by r, get r sine theta. This is x squared plus y squared equals x, well, equals y, right? Because y is r sine theta. So x squared plus y squared minus y equals 0. X squared plus y minus 1/2 squared equals 1/2 squared. So basically this is a circle centered at 0, 1/2 with radius 1/2. So this is a circle sitting on top of the x-axis. Clearly from this picture you can see my horizontal tangent lines happen at the origin. My vertical tangent lines happen here. So you could check your work if your thing is easy enough to sketch. I don't know if I'm forced to put this on a final. I don't know if I'd put one where it's easy to sketch the answer. But it'll be a nice check. Like on your fourth exam, I'd probably put one where you can sketch the answer and double check your work. Any questions?
When is the fourth exam?
Thursday. Right, and the final is the 20s. It's on the syllabus, right? And it's in this room. Yeah, the last exam is the last day of class. Let's move on. Areas and length, right? Arc length and area. Two important things we need to know from calculus. What if we're given polar curves? How do we do that? I don't know if you remember this formula from algebra. I'll just tell you what it is. So if we're given a sector, so we know that that's r, and this is the angle theta that extends that sector. What is the area of this sector? Where theta is in the radius, theta is in radians. It's like 1/2 r squared theta. Look up the formula. Do you remember what the formula is in degrees? You take theta over out of 360, right? It's because the full circle is 360 degrees. You take the part of 360, then multiply by pi r squared. Right? Remember here, theta in degrees, you might remember that formula. You take how many degrees out of the 360 you're using, and then multiply by, that's the proportion of the area of the circle, right? Pi r squared. But we know to convert from degrees to radians, you multiply by pi over 180 over pi. So this cancels that, and you end up with that. Now thinking of this guy in radians, you end up with this one. You did that in pre-calc, just don't worry about it. So that's the formula. We're just going to use that formula. In polar, we generalize this idea, right? So let's say I'm on the xy plane, and I have this random polar curve over here, like my r equals f of theta doing whatever it's doing, right? Then I measure between two angles, right? Say a theta 1 and a theta 2, right? So this angle here is I can think of as delta theta, right? The change in theta, right? Here my r was always constant, so in this formula my r is just a constant function, but here I think of it as r as well, but now my r is varying. So then here I can think of a as 1/2 r squared delta theta. Right? If I cut these into very small pieces, make the Riemann sums, you can sort of see where this is going. This means for hence we obtain the area under the graph r equals f of theta is given by of 1/2 r squared d theta. For my theta values falling between this guy and this guy. This you need to memorize. Right? So you integrate 1/2 r squared. D theta is just like my change in theta from this angle. The idea is I do that whole Riemann sums approach where I don't cut this up into rectangles, I cut it up into many fine pieces of sectors that look like this. And then I just use this formula for each part that has a width of delta theta. And then you use Riemann sums, add those all up, your delta theta ends up becoming your d theta, and that's that. Area between curves are similar. Let's also mention that. So let's say I have one curve here. This is r equals f of theta. Another curve here, which is my r equals g of theta. And I'm measuring between these two thetas, and I want to find the area between these guys. For angle theta 1 and theta 2, what do you think the area is going to be? You subtract them, right? 1/2 theta 1 up to theta 2 of the outer one, the bigger one, right? Like the top function. F of theta squared minus g of theta squared d theta. You can sort of think of this as 1/2 times big R squared minus little r squared. Right? Your outer radius squared minus your inner radius squared. Concept we've seen before when we were doing volumes. Okay, let's do some examples. Right, so what we really need to memorize is that. Right, so you know that, you're good. If you forget that, you'd have to remember this and sort of build it back up. Which is not entirely unfair for me to require. Guaranteed to come in your final and your next test, this kind of question. In fact, I probably grouped them together. So one thing you can expect is something like, I can say, sketch this polar graph and then tell me what's the area inside one of the loops, right? That's a fairly straightforward question that you'll see all the time, right? So let's do one. Find the area enclosed in R2 plus 2 cosine theta. tell me what this might look like? It's going to go up to 2, then go up to 4, and then down to 0. So I'll have that into 4 pieces. It's a cosine, which means it's going to look like this. Which means ultimately my graph would look something like this. Radius 2, radius 4. This is 0, pi over 2, pi, 3 pi over 2, 2 pi. At 0, I'm on the circle radius 4. Then I jump to the circle radius 2. Then I jump to the origin. Then I jump back to the circle radius 2. Then jump back to the circle radius 4. So this is my graph. Right? Sideways card. I think they call this a cardioid. Okay. So I want you to tell me what is the area of love. Well, love this big. I don't know what you want to call it. Okay, so notice that 0 to 2 pi takes me around the whole curve. So I can just find the area by integrating between 1/2 the integral of 0 to 2 pi of, remember, r squared d theta. My r in this case is this. Just plug it in. 2 plus 2 cosine theta squared d theta. So how do I integrate this? Distribute, expand. So you have 4 plus 8 cosine theta plus 4 cosine squared theta. Theta. This guy's going to go to 0, remember, because we're integrating over a full period, so I can ignore that. 1/2, 0 to 2 pi, 4 plus, this guy would become what? 2 plus 2 cosine 2 theta by applying the half angle formula. This guy's going to go to 0 because I'm integrating over a full period, so I'm really integrating 6. So this just means I have 1/2 times 6 theta between 0 and 2 pi, which gives me 6 pi. Which is the area of love. Who would have thought? That's sort of it. So remember, as that formula, apply the formula. It's kind of like the arc length situation. You know the formula, you plug it in, and you have to remember how to integrate trig functions. Hopefully you remember that. Okay, so here's a nice one. So this is a nice problem to ask on an exam. Find the area inside the inner loop of r equals 1 minus 2 sine theta. So now we have to figure out the bounds for the inner loop, basically. So again, we're just going to do our quick sketch. We have 1, amplitude is 2, so it's going to go down to -1. It's going to go up to 3. It's going to be my guy here. Lopsided. Boom, 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 boom. It's a minus sign graph. It's here, here, here. You need to know where those zeros are. So I'm going to find it. 1 minus 2 sine theta equals 0 means that a half equals sine theta, which means my theta is going to be pi over 6 and 5 pi over 6. Those are going to be my two zeros. Now, a little trick here, you can actually stop here because that's actually going to be the answer you want. Remember when loops happen, right? Loops happen when you start at a 0, you go somewhere else, and you come back to the 0, right? So, pretty much starting at a 0 here, and doing this big thing and coming back to the 0, that will give me a big loop, right? Starting at 0 and do a little loop, come back to the 0, get a little loop, right? Obviously, if I have a big loop and a little loop, the inside loop must be the smaller one. I know the limits already. I don't even need to go further and draw the polar graph. I just know at this point, my area is just going to be 1/2 the integral from pi over 6 up to 5 pi over 6 of r squared d theta. One minus 4 sine theta plus 4 sine squared theta d theta. I can't assume this goes to 0 because we're not integrating over a full period, so I have to bring that with me. 1/2 times pi over 6, 5 pi over 6, 1 minus 4 sine theta. Use the half angle formula on this guy. I'm going to get 2 minus 2 cosine 2 theta, d theta. This 2 and this 1 I'm going to add, and I'm going to make them 3. So I'm really integrating that. So the integral of 3 is 3 theta. Integral of 4 sine is minus 4 cosine. Integral of 2 cosine 2 theta is plus minus 2 sine 2 theta, minus sine 2 theta. Between pi over 6 and 5 pi over 6. Alright. So I'm going to plug in 5 pi over 6. I get 15 pi over 6 plus cosine pi over 6 is what? Cosine 5 pi over 6 is what? Alright, 5 pi over 6 is in the second quadrant. My cosine is negative. Negative what? Radical 3 over 2. Minus, plug in 5 pi over 6 in here, I get 5 pi over 3, sine of 5 pi over 3. 5 pi over 3 is in the second quadrant, so what's sine of pi over 3? Huh? It's again radical 3 over 2. Minus, now I'm going to plug in pi over 6 here, it's going to be pi over 2. Plug in pi over 6 into cosine, cosine of pi over 6. Plus 4 radical 3 over 2, so it's 2 radical 3. Plug this guy into here, 2 cancels into the 6, I just get pi over 3, sine of pi over 3. It's again radical 3 over 2. 1/2, I think I wrote down this answer. Well, ultimately, you should get pi minus 3 radical 3 over 2, I think. Let's do another one. Find the area inside one leaf of r equals 3 cosine 3 theta. Again, so we do our preliminary sketch. I know the amplitude is 3. Cosine 3 theta means this is going to cut into 3 sections between 0 and 2 pi. And I am going to have 3 cosine graphs happen. There's one cosine graph will happen here, another one here, another one here. And again, we've done 3 theta many times. This is going to be pi over 6 and 2 pi over 6 and so on and so forth. And here inside one leaf, remember a leaf is just when you go to the origin and come back to the origin. Several ways you can do it. You can actually go between 0 and pi over 6. Notice that you have a half a leaf, right? So I can literally double the answer between 0 and pi over 6. That's going to be double 1/2 integral 0 pi over 6 of r squared. Alternatively, I could have not doubled and just do pi over 6 to 2 pi over 6, and I'd get the same answer. The answer to that is actually 3 pi over 4. I'm not going to do it. It's trivial at this point. I mean, after the integrals we were doing in chapter 6, these are like... Here's a nice problem. I'll end here. We'll talk about arc length next time. Arc length is just going to be, again, a formula that you just plug in the chug. Maybe I can tell you the formula for arc length, and you can do it on your own. And then we'll do some more examples next time. Because you'll need it for the test. Let's see. Here's another one. This is another nice test problem. I've seen problems like this on finals before, several finals. I don't remember if I put a problem like this one in. I don't think I wrote one like this, but I could be wrong. Because I saw it a lot. Find the area inside. They give you 2 graphs to worry about. R equals 2 plus 2 cosine theta. But outside, R equals 3. Did you graph this guy before? He looks familiar. You didn't? I thought that was the heart. Yeah, where he was. It's not the same. Right, there's one where the radius was 2, there's another one where the radius was 4, and at 0 we started here, and we went boom, boom, right, so that's one guy. What does r equals 3 look like? It's just a circle of radius 3, right? What area do I want? They're inside the heart, but outside the circle.
Sliver.
It's this guy. Right? So basically what I'm going to have to do is I'm going to figure out what are the theta values that bounds this region, right? What's my theta 1 and my theta 2? That are my boundaries for that region. But what has happened here? Intersections. So I'm going to have to find intersections. So I'm going to have 2 plus 2 cosine theta equals 3, which means cosine theta equals 1/2, which means my theta, the first one, cosine theta equals 1/2 when theta equals pi over 3, and this guy would be, I think of it as minus pi over 3. It's very important, I don't think I mentioned this, but it's very important that limits must go in increasing order. So I always want to go from the smaller angle up to the larger angle. So if I had put 5 pi over 3 on the bottom, and then pi over 3 on the top, that would cause problems. You'll actually be finding the opposite angle. It'll be weird. So you want to think of it as the smaller angle. So this you think of as minus pi over 3. And so the area here would be 1/2 the integral from minus pi over 3 up to pi over 3 of, remember how we find the area between curves? Outer radius squared, which is this guy, minus the inner radius squared. Is that guy? Do that on your own. It's not a big deal. Arc length, I'll just tell you the formula, try it on your own. Similar to before, your length would just be the integral from theta 1 up to theta 2 of the radical of dx d theta squared plus dy d theta squared d theta. It turns out though this can simplify to something else if you care to even do it. Personally, I wouldn't care to do it, but it'll be less algebra if you bring it to this stage. This simplifies to I think it's like r squared plus dr d theta squared.
So if you don't have things in x and y, you just use that.
Yeah, so if you don't know the x and y, we can change the dx d theta and the dy d theta into the equations we had before, and it will basically simplify into this. So yeah, that's the last thing I want to mention in 9.3. I was going to do an example of this, but it's pretty straightforward. Next time we'll talk about the homework for that, and we'll actually finish the last 2 sections. I'll have a handout for you guys. 9.3 is due. Just 9.3. No, wait, 9.4. This is 9.4. 9.3 and 4 due Tuesday.